Hello, and thank you very much for following out. Let's continue with the elbow tutorial. So as you see, we're adding more things while we keep advancing, moving forward. So in this case, what we're going to do today is just to work a little bit with boundary conditions. So we're going to play with different combination. In the previous tutorial, we saw that by adding the pressure boundary condition, we can get a parabolic profile. In this case, we're going to implement a paraboloid profile here, but also we're going to set up the combination, the pressure and velocity combination here. Also, we're going to add a source star here somewhere in our mesh, and then we're going to run the simulation. So previously we saw how to add source star, positive scalar in the boundary patches. So now we're going to see how to do that also in the internal mesh. But to program this boundary condition, so the starting point, you need to write down your equation. So this will be our equation, and we're going to set that in this patch, in the inlet patch. So basically, to program this boundary condition, we're going to use what is called codeStream. This is a capability, something that let us program direct in the dictionary. Okay, so where you have u, p, or whatever variable you want, you can directly program there. So here, do not be afraid. It's not that difficult. This, you can take it as a template. So you open your dictionary and you will basically copy and paste this text, and the only part that you need to modify is this one, the code section, where you need to put your equation. Okay, so basically this is our implementation. Okay, so look at that. Basically, again, this is very much can be in the standards. Here you initialize your field. Here we declare a constant, and then this is how we access the patches. Okay, so here we're accessing all the patches information and everything, and then we implement the equation here. So we do our loop. Okay, this is how the loops are done in OpenFOAM, but you can do it also in the traditional way, also in C++. So you implement this equation here, and then this last step is the one that will write that information into the dictionary. Also will let you plot those results using Paraview. Okay, so as you see, it won't be very difficult. I hope also we're going to go fast through this. So basically, again, you download your cases, and now you go to your zero folder, and we can open UMP. Okay, so we're only going to program for U, but to program for an scalar, a U, which is a vector, to program for a scalar pretty much is the same, but you need, instead of declaring vectors, you will declare a scalar. So as you open U, you will see that we have this, and at the beginning in inlet 1, here's where we want to implement our boundary condition. Okay, so as you come here, you will see that pretty much the beginning here, this is what I was telling, that this is pretty much a standard. Just copy and paste this one, and then the only part that you will need to modify is the part where you have the code section, and not everything. For instance, here at the beginning up to here, you can leave it as a constant part. Okay, copy and paste. This is how you access that dictionary and also the mesh information and the boundary mesh. Something really important. Okay, depending on how you name your boundary, your mesh, the patches, you will need to change this keyword. Okay, usually no, it have to be the same and this one. Okay, so if the name of the patch is inlet 1, just put it here in inlet 1. If you don't do this, you will get a compilation error, and maybe you are not good in programming, you haven't programmed anything, it will be difficult to track that one. So here you need to deal, even you need to deal with compilation. Okay, it's very straightforward. Then here we initialize. So pretty much this is a standard. Remember, if you're working with a scalar, here you will write scalar field, the name is scalar, probably you will call it P, and here instead of initializing a vector, you will initialize a scalar, and you will put value here. So nothing changed. Okay, so let's go back here. We declare a few constants. See that those are scalars. These are the constant that comes into it that I'm going to use into my equations, and then our for loop. Okay, this is how we access information in the patch, and if we work with internal cells also, this is how we are going to access all those cells or faces or whatever you want to access. And then here is how we access the coordinates. So see that we access x, y, and z coordinate. In this patch that we're working, we want the phase center, and this is iterate in this phase number in this direction. So this 0 will correspond to x, 1 to y, and 2 to z. And then here's our actual implementation. Okay, so this is what we have here. So we have our equation here is a vector, and we only want out the paraboloid in the x direction, and here how we implement it. So pretty much is, as I mentioned, is this equation here. Is translated here. I didn't put here the minus coordinate to translate the other, but here we have the equation. Minus c is the x or the y, whatever your reference system. Okay, and then a few constants, and this will be our implementation. Okay, so if you want to check this implementation, you can go and you can see that right ahead in your case. So for instance, select the inlet patch. Okay, and voila, this is our boundary condition. Let me go to times 0. Okay, so this is the pressure. No, sorry, we need to. Okay, and let me color. Okay, no color. So you see the velocity distribution, the paraboloid, and the vectors normal to that patch. And also we can change that, and I can say that I want to scale using vectors, and this is how we have our paraboloid patch. Okay, as you see, pretty easy to implement that one. Okay, so we don't need to deal with the pain of programming in OpenFOAM. That can be really tricky. So copy and paste that dictionary and then just implement your equation. So let's keep reading this dictionary, because also in inlet 2 we have another profile, another boundary condition, that we're going to have a parabolic profile in this case, but it will be a natural one. Why? Because we're using a pressure boundary condition that will let the flow evolve in a natural way. So that one will be this patch here. So as you see at the beginning, velocity is 0, we're imposing a pressure boundary condition. So this is important to know the combinations on to set up boundary conditions. So most of the time it's better to impose pressure. Sometimes you would like to impose velocity, it's up to you, but pressure and mass flow boundary conditions are more robust than velocity boundary condition. In this case, look at that. For velocity, we impose a pressure, normally the outlet velocity. Probably the naming convention can be difficult to understand. It's not very intuitive from the name, but basically this boundary condition, what it's doing is computing velocity from the pressure. And remember that we have the documentation. So if you go to the OpenFOAM website, then you see here boundary conditions, and in boundary condition you can access all boundary conditions. So for instance, I already have this one, and here you have how to use that one and when you can use it. Okay, so you impose this one. For velocity we need to, for pressure we need to set the velocity. Okay, so in this case we need to play around with total pressure. So as you go here, you see that we have total pressure, and here you have the different combinations. So basically when we're going to use total pressure for incompressible succinate, so basically this is how you use it. So we need just to give the static pressure, and from that one OpenFOAM will compute the total pressure, and then the velocity will be computed from this one. So your velocity profile will be a natural profile, not the imposed one. Okay, so this was so far to what refers to this boundary condition for U and P. Okay, and then let's talk about something else, because as I told you, what we're going to do here as well is just to add a passive scalar, but inside of this domain. In previous tutorial we had something, okay, that was in the boundary patches. But look at what we're going to do here is that in one point we are going to add in a selection of cells. See here, I think the starting point, I'm going to show you also that, because also you can choose when to add this scalar. I think it's from 1 second. So in this cell selection, okay, you see that we have this cell selection here. So remember, it's 3D. We're going to add a scalar here, and again we have S1 and S2 entering in the other patches. So we're going to see how everything is mixing. Okay, so if I go to time 80, yes, I think that all these scalars reach this point, so we can see how everything is mixed, and then also I can control the concentration in the outlet. And I think if I would recall at time 80, I switch off this scalar. So if I go to 90, we're going to see, whoops, you see, okay, yes, here I switch it off, and you see that now the scalar, we don't have any more the scalar in the domain. So you have a lot of control when it comes to a source fvOptions that we're going to talk about this here. So let's go, now that we talk about boundary conditions, let's go into the dictionary control data. Okay, this is, remember, here's where we set the pluggable solver. So we already studied previous tutorial how to set up for scalar 1, scalar 2, but this is set in the patches. Okay, so we create this one, we set the boundary conditions, and then we let it run. But now let's add a source scalar, but this scalar is not set in boundary patches, it's set in internal cell. So pretty much this setup is the same. Okay, you give it a name to that scalar, but then we're going to use fvOptions. Okay, so these are sources that we create and are already plugged with the solver. So in all versions of OpenFOAM, sometimes you have to program the sourcer. Now it's really easy using this dictionary fvOption, where you can call over all this scalar. So again, we're creating this scalar fixed value constraint. I have a fixed value. Okay, will start at time 1, it will last for 8 seconds, so up to time 9, and then I will apply this source in a cell zone. There are many selections, so you can select points or cell sets, whatever. So here I created the cell zone, I gave it a name, source 1, and here I will create this field value. So we created S3. I will put here the value 1, 3. Remember that in initial conditions, you need this scalar here, but here everything is 0 gradient because we don't have it in patches, we only have it internally. And the next step is how to create these topological selections, okay, of cells. So there is another dictionary that you will find in the system folder. Okay, so in your system folder you will have the toposet dictionary. So as you go here, it's here where you do that selection. So see that what we're doing is creating a new selection. Okay, we call it source 1. It will be a cell set, it is a new one, and the source will be box to cell. Okay, I will create a box, and with this box we'll transform it into a cell set that will contain all those cells. Remember, as you misspell something here, you will get all the options available. There are many of them available, by the way, so just play around with this one. So here I'm giving the coordinate of that box that I want to select, so it will be a box here in 3D that we have there, and then this will create a cell set. This cell set can be used because fvOption can take a cell set, but also we can convert this cell set into a cell zone. Also, you can use a cell zone for source 10. So to do that conversion, you just give it a name, can be the same name, and we'll say that I want a cell zone set. So new one, and how the source will be a set to cell zone, a set of cell cells. Okay, so this cell set cell we convert it to a cell zone. I know it's a little bit confusing, but just play around with this one, you will get the idea fast. So buses then are valid to apply this function object, the fvOption. In this case I'm going to use this one, it's my choice, it's up to you if you want to choose another one. but also remember that that information can be accessed here. We can access that information. So let me open a new tab. Okay, I will open ParaFOAM, just not to have to many things open, and see here that you have to include sums and sets. So I want to include everything. Okay, it will take a while to load the mesh, I guess. So now that we have the mesh, okay, let me put the wireframe, and then we can access those cells on our cell set. So I will access the cells, and remember they're the same, and apply, and see that we have this cell selection, and in this cell selection I will add a source state, or I can do whatever I want. Okay, so you can do whatever you want with that one. You have a lot of flexibility in what you want to do to add there. So basically this is what we're going to do. We have a paraboloid profile here with a scalar. Here we have a pressure boundary condition as well with a scalar. Here we're adding a sourcer, okay, another different scalar, and we have plenty of function objects all around to monitor things, which are really handy. So here at the outlet I will have one that is monitoring the maximum values of all my scalars. Okay, so I already run this simulation. Okay, so we're going to see the results. But for instance, if we check the post-processing, you will see that we have many functions objects. And for instance, here we have the outlet max value. And if you open this one here, you can access the maximum values, whatever you are monitoring. In this case, we're monitoring UP and S1, S2, S3, the maximum values. And here you can see the concentration. So you can just follow the evolution in time. So as you see, S3 will start to enter the domain at time 1 second, as you see here. Then the concentration will start to increase into the domain into up to 9 seconds, and then you will stop that concentration. Okay, and then the other two scalars are entering continuously into the domain. You have it as well always, but see that you can use, it's very handy not to monitor everything. So here we know precisely the concentration in a specific patch. Also you can do it in a specific region of your domain. Here we have the mass flows, okay, inlet and outlets. Remember, the method is fully conservative, so whatever is going in is going out as well. So the summation at the end should be 0 or close to 0. So remember, the numerical method produces certain amount of garbage that we need to live with that. So not precisely you will get 0 in that difference, and but many others functionality. So I highly advise you that set up your common function objects. Okay, so here for me it's pretty much a standard to always set up minimum and maximum values and also mass flows if I need, and also some monitors point, but it's up to you. So the setup is pretty much the standard, nothing change. As we skin again, as we have a new equation, we need to add how to discretize this one, and see that you can use different methods for different quantities. So here that in S1, S2 we use cell limit Gauss linear, and then for S3 we use least square. So there is no problem in mixing and having different methods. The ideal is to have everything standard, but again, very problem dependent, and you will need to run your own setups and tests and benchmarking, and then SB solution. So if you run this case, you will get your typical output. And for instance, let me run this one and again you can run in parallel with no problem. Let me run this one for a few iterations. Okay, so I will go icophone and see that at the beginning you will get this message. This message means that it is compiling automatically whatever you program in your dictionary. Remember, you can program that one in any dictionary. In this case it's within UMP, and then you have all your passes with scalar, everything is computed, and then you start to solve everything. And then as you go to S3, you will see this funny message that you have a solution singularity. Remember, when we set up this case, And sometimes this is not a good idea, but I know that in this case won't be a problem setting every boundary patch as a zero gradient, because you have a very ill-conditioned system, so it's a singularity and this is what you're getting. But here there is no problem, we're not entering anything. So at one point when we inject the scalar, that message will disappear. So for instance, let me show the previous log file. Okay, so we run the simulation, we have this log file, and then solution singularity. See that here we don't have any more that problem. Okay, see that at the moment that we inject that scalars, we're now solving a system. We have the values in the outlet, so it's a well-conditioned system. Okay, so just to show you a little bit some more post-processing, like in the previous cases we have many things, but just to show you, we already saw in okay, let's see both profiles in the patches. So I go, let me enable just inlet 1. Okay, so see that even if we didn't set up that paraboloid profile, we have a paraboloid here. No, that profile, because it's a natural evolution, the velocity profile due to the use expression. But instead, this one, it is imposed, and we program, and then we can just plot the vectors. Okay, so let me change this uniform. Let me hold points. So we have our paraboloid there, and then also we have this boundary condition here that is a natural one. Okay, then let us plot the size there. Okay, against the one you can just check, but the vectors in this plane, okay, will take a while. We have many cells there, so it's loading slowly everything. I hope it won't crash. Okay, it's a little bit intensive, this post-processing. There are many cells there. So okay, stop there. Okay, so if I switch it off here, okay, okay, so here see that we have the velocity vectors, okay, and the cut plane. And then we can also check the different scalars that we have there. So we have S1, S2, and S3. Okay, that's entering there. And probably we can do another operation. So for instance, I can get a calculator there. I call it results. Okay, and I want this one to be equal to the summation of S1 plus S2 plus S3. Okay, so here we're doing this post-processing inside ParaView. Also, you can do it in OpenFOAM. There are a few functionalities that will let you do this kind of operation, addition between different fields, and then create new fields. Sometimes it's faster to do it directly in OpenFOAM. Depends on the complexity of what you want to do. So as you see here, we create this new scalar. So pretty much we have this, and you see that okay, it is unbounded. Actually, it's a little bit oscillatory. Okay, so here we have 0, scalar 1. Then no 1, here we got scalar 1, scalar 2, and then the scalar 3, which have a really high values, becoming unbounded. Okay, so probably it will be better to use a different numerical scheme, a high resolution numerical scheme to avoid that unboundedness. So see here that it's very unbounded here in this time, and then at one point we're having unbounded values. That we can check that again. We can check that information as well, saving all those function objects. We can access that in min max domain. So if I open that, and I think I will save in that, we can see where we have, okay, see that we have S3, and we can see what is the max minimum values of S3. So for instance, S3. So there, well, then you will need to use your program to clean out, get your tidy data. We use Python or R to do that one, to check everything. So that's all that when it comes to post-processing. A little bit more complex than the usual one we have been doing, and we just study how to add a new source state, internal one, how to program a little bit boundary conditions, and I think that is all for this case. We have played a lot with this one. I hope you find it useful, and just keep in touch, and we always update the cases. So maybe we're going to add a new session to this one, a new video. So probably doing some optimization, moving this pipe here using on shape. So thank you very much for your attention, and enjoy. Bye.